Section 3.7 is implicit differentiation. There are times when we have a function that's defined implicitly. What that means is this equation defines this graph that is really made up of three separate functions. You can see that the graph as a whole is not a function. It does not pass the vertical line test here, or many places. But if I break it up into the first function, actually they call the first one from A to O, and the second function, and the third function, we have three functions that combine together to make an implicit function. In other words, we have a graph, but we cannot define it explicitly. We cannot write it as y equals something. So therefore, we need to use implicit differentiation. So to find the derivative of this function implicitly, first of all, we need to know that when we are finding dy dx, that means that we are taking the derivative with respect to x of y. So if I have y equals 3x plus 1, I'm taking d dx of y and d dx of 3x and d dx of 1. D dx of y cannot be defined other than by saying that it is dy dx. It is the derivative of y. Excuse me, let's go back. Over here, we have 3 plus 0. So when we differentiate y with respect to x, we get dy dx or y prime. When we differentiate x with respect to x, we get 1. So d dx of x is 1, d dx of y is dy dx. So we're going to use that information to do our implicit differentiation. So dy dx of 3y squared plus 2y plus 5x. To find dy dx, differentiate both sides of the equation with respect to x. In other words, find d dx of both sides, treating y as a differentiable function of x and applying the chain rule. So let's see what we need to do. So here's our function again. So taking the first function, the derivative of that using our power rule is 6y times chain rule, because the inside function y has to be differentiated as well. So the chain rule, again, says here, actually, I don't like this notation. Let's ignore that for now. The chain rule says I take the outside function, 2 times 3 is 6, so 6y to the first power is the outside function, and then I differentiate the inside function, which is y, with respect to x. Here, the derivative of 2y is 2 plus dy dx. Here, the derivative of 5x is 5, and if we want to say it this way, we are looking for dx dx, but that's just 1, so I don't have to write it. All right, so let's keep going. I'm going to factor out the dy dx, which gives me dy dx times 6y plus 2 equals 5. Since I want to solve for dy dx, I divide both sides by 6y plus 2. Okay? Let's try it again. Well, first of all, let's talk about this. So first, differentiate both sides of the equation with respect to x. Collect the terms with dy dx on one side of the equation. Factor out the dy dx and solve for dy dx. So that's our implicit differentiation process. This is used a lot for lenses, which are really parts of ellipses. We can find normal lines, the point of entry to a lens, the tangent, and then we can talk about the light ray as it enters. So we're not going to do too much with this, but we are going to look at normal lines and tangents. So let's find the equations of the tangent and normal line through the graph given by this function. Now this is an ellipse function. And we want to do all of this at the point root 2 over 2. So the first thing to do to write an equation, since we already have our point, we need to find the slope. The slope is y prime, or dy dx, evaluated at root 2 over 2. So that's how we find our slope. So using our implicit differentiation, d dx of x to the fourth plus d dx of x squared y squared minus d dx of y squared equals 0. So we've got a lot of things going on. Let's look at the first thing. Now this is all in terms of x, so all we have to do is use our simple power rule. Bring down the 4 and raise it to the third power. So that's the first piece. This one's a little more complicated. We need a product rule. So the first times the derivative of the second, d dx of y squared. So that's 2y using the power rule times, using the chain rule, y is an inside function here, dy dx. So derivative of the first, the first times the derivative of the second plus the derivative of the first times the second. Product rule, chain rule, implicit, minus, again, this is with respect to x, so we're going to need our chain rule. Bring down the power, 2y times the derivative of the inside function is dy dx. So remember, x squared, y squared must be used the product rule. All right, so we've got a little bit of work to do here now to get our dy dx isolated. So any term with a dy dx is going to stay on the left side. Everything else is going to the right. So 2y times I would do an in-between step here. Let's look at this. I'm going to bring my negative 4x cubed, subtract that from both sides, minus 2xy squared. So I'm moving both of these to the right. On the left, I'm going to have 2yx squared, this piece here, minus 2y, this piece here, and both of those are times dy dx. So then they also factored out a 2y, bringing us to this step, and on that side they factored out a 2x. Now I'm going to bring everything to the other side by dividing everything by 2y, x squared minus 1, and then we can also cancel the 2's, bring the negative side in front, and that's the slope of the tangent line. So far we have found the slope of the tangent line. Now, I need to find this slope at root 2 over 2. So there's my equation for slope. So plugging in root 2 over 2 looks like a mess, but remember, these two will cancel. 2 times root 2 over 2 squared is 2 times 2 fourths, plus 2 fourths, 2 fourths minus 1. So simplifying this, I will get 3 halves over negative 1 half. Don't forget your negative sign in front, so that becomes positive 3. So my slope is 3. My point is root 2 over 2, and now I want to write an equation. Tangent line, y minus y equals mx minus x. They then simplified. The normal line, instead of using 3 for my slope, I'm going to use negative 1/3. Same thing using the point root 2 over 2. All right, there's quite a bit here. We are going to do some more practice before I let you loose on problems. And then they cleaned it up even further, sorry. So let's do this again. One more example for your notes. We want the second derivative now. So first we find the first derivative. Differentiating each term with respect to x. 2x plus 2y dy dx equals 0. Moving the 2x to the right and then solving for dy dx, we get negative x over y. That's the equation for my first derivative of this function. Differentiating again. So now I need the quotient rule. Low d high, and notice that the minus sign is still in front, don't forget that, minus high d low, the derivative of y with respect to x is dy dx, over the square of what's below. Now, this looks fine, except this looks a little messy in my equation. So all I'm going to do is substitute what I found here down here to put everything in terms of x and y. Continuing to clean it up a little bit, y squared minus or plus x squared over y, and then again I would like an in-between step here. So I've got y plus x squared over y squared. Let's get a common denominator on top by multiplying this by y over y. So now I have y squared plus x squared over y squared. Bringing that y down brings me to this. So there's my second derivative. So power rules for rationals, we have already done this. This is exactly the same as any power rule. d dx of x to the n equals n times x to the minus 1. It works exactly the same if we have rational powers. X to the 2/3 equals 2/3 x to the negative 1/3. And we've already done some of this. So that's it for this. We are going to do some more. Go back and look at it one more time to make sure that you follow the steps that I did on the two examples here, and then we'll do some more in class.